Okay, so in this video, we're going to talk about the exact arrangement of electrons in a specific atom. All right, and so how, if we're looking at an atom and we're looking at their electrons, where are those electrons according to what we talked about in the last video? This diagram that we're looking at is what we call an orbital diagram. Now, orbital diagrams help us to visually see where the electrons are in an atom, okay? And so just to kind of highlight a couple of things that this orbital diagram is showing. All right, so to the very left here, we can see that this orbital diagram is increasing in energy as you're moving up. So as you're moving up, the amount of energy that the electrons are using in any particular shell or subshell is increasing. All right, so what does that mean here? So when we're looking at this, so an electron that resides in the 1s will use less energy than electrons that reside in the 2s. Electrons that reside in 2s will use less energy than electrons that reside in the 3s. And so on and so forth. So as you move up, the amount of energy that the electrons are using, or in this case, is increasing. Okay, so that's one thing. Another thing that you should see in this case is the shell and the subshells annotations. All right, and so remember when we talked about in the last unit, or the last video, I'm sorry, that you have your shells, all right, and then the shells have these very specific numbers that goes with them, all right, and then so the numbers for the shells is actually annotated in this orbital diagram, and it's annotated by these numbers that we see here. So I'm gonna kind of blow this up. So we have 1, so that's showing you the first shell. Then we have 2. These 2s represents the second shell. Then you have these 3s that represents the third shell, okay? Then we have 4s represents the fourth shell, and oh yeah, well, there's one over here is one this far end corner, and then thus 5, 6, and then it goes on to 7, 8, whatever cases. I mean, there's legit unlimited number of shells, but we're only really going to stick with probably the first 7. Okay, and so these numbers represent the shells. Now we also talked about that the shells also are divided into subshells, and we said that there's at least 4 subshells that we're going to worry about in this class. All right, and then if you see here, you see these subshells. All right, so we have your S subshell. All right, then you see the P subshells. All right, then you have your D subshells here, and then last you have your F subshell. Okay, so these are different subshells that the orbital diagram actually shows. Now, another thing that I want to illustrate, or at least make connection with from the previous video, is what subshells exist in which shells. All right, and so we kind of drew out this table here where we have our shells. All right, their shells number, then we have our subshells that exist within that shell. All right, and then we even looked at, so here we have a number of orbitals, right? And then we have the maximum number of electrons. Okay, so the point of this is just to make sure that we can make a couple of connections from the previous video, as then we're going to move on to orbital diagrams, and I wanted to make sure that you could understand, you could see the relationship, and we're just not making things up. All right, so shell number 1, right? Shell number 1, we said that the only subshell that you could find in shell number 1 is your S subshell. How many orbitals does the S subshell contain? Is you only have 1 orbital, okay? And then it has the maximum number of 2 electrons in this case. Now, if you're looking at the orbital diagram, these circles represent an orbital, right? So here's your first shell. That's what that 1 stands for, all right? And then you have that sub-level or subshell, S, all right? And the S only has this 1 circle, which is the orbital, all right? So this is the way how we kind of put this together. In shell number 2, in shell number 2, you have 2 subshells, right? You have subshell S, and then you have subshell P, right? Subshell S has 1 orbital. Subshell P has 3 orbitals, right? And so now if you look here, we could see that. Here's our second energy level, right? It's labeled 2. The first one is subshell S. Subshell S has 1 orbital, so that's why it's only 1 circle. And then subshell P has 3 orbitals, and this is the reason why you see 3 circles. Okay? Now, when we're talking about the maximum number of electrons, well, think about it. In subshell S, we can only have 2 electrons. All right, in subshell P's, if you count up all the orbitals in subshell P, you can have a maximum number of 6 electrons, because remember, each orbital could contain 2 electrons, maximum number 2 electrons. And so if you were to add this up, you have 8 electrons. The third shell, all right, and so when we're looking at the third shell, we see that, okay, so when the third shell here, we'll kind of circle it so we can highlight and see where we're talking about. All right, has subshell S, has subshell P, and has subshell D, which are 1 to right in green. All right, and subshell S only has 1 orbital. Here's our 1 orbital for the 3s. All right, shell 3 subshell S. Your P or subshells, or your 3p specifically, has 3 orbitals, and then your 3d has 5 orbitals. All right, and so when we're trying to calculate the maximum number of electrons for your S subshell or 3s subshell, there's only 2 electrons could fit in there. For your 3p subshells, you could have a maximum number of 6, and for your 3d subshell, you have a maximum number of 10. And so if you add that up, we have 18 electrons, okay? Now, when we're looking at the 4th shell, okay, and to highlight the 4th shell is here. So here's our 4th shell. All right. Now, the 4S sublevel. Here's our 4S sublevel. All right. Circle this in red. You also have your 4P sublevel. Okay, so that's, you have P here. Then you have 4D sublevel. And then you have lastly 4F sublevel. All right. In the 4S sublevel, you have 1 orbital. In the 4P sublevel, you have 3 orbitals, like all your other P's. For your 4D sublevel, you have 5 orbitals. And for your 4F sublevel, you have 7 orbitals. Okay, and so if we were to try to figure out how many electrons can fit in the 4 shell, all right, the 4th energy level, 4S has a maximum number 2. 4D has a maximum number 6. 4P has a maximum number 6. 4D has a maximum number of 10. And 4F has a maximum number of 14. And so if you were to add up all these electrons, you'll get that there's 32 electrons. Okay. And so that's the way that you could kind of, that you need to interpret this orbital diagrams. All right. And so hopefully you can see the connection between what we talked about last class when it comes to just the shells, the subshells, the number of orbitals, and the number of electrons, okay, with this orbital diagram. All right. Now, let's put this into practice. So there are 3 rules that electrons follow when it comes to filling up this orbital diagram. All right. So the first rule that electrons follow is what we call Aufbau's rule, right? And so Aufbau's rule basically states that electrons, all right, fill the lowest energy shell or orbitals possible or available. So this simply means if, let's say, you have this atom in its nucleus and it only has 1 electron, where would this electron be? Will it be in the 4D space? Will it be in the 3p space? Will it be in the 4f space? No, the electron's going to occupy the lowest orbital possible, meaning this electron will be in the 1s. Okay, remember, this orbital diagram is showing you an increasing energy. So the lower the shell number, the lower the energy. All right, and electrons will like to use the least amount of energy possible. Okay, and so this electron, which I ended as an arrow here, all right, is going to be in the lowest energy possible, the lowest orbital possible, and this orbital is the 1s, the first shell, and the only subshell that's in the first shell is the s. All right, and s only has 1 orbital, so there it is. The second rule is what we call Pauli's exclusion principle. All right, and so this rule basically says that each orbital can hold only 2 electrons, okay, which these electrons must have opposite spins. All right, and to show that these electrons have opposite spins, what we basically do is like, okay, for this case, if I want to put 2 electrons in my 1s orbital, then I'm going to have 1 electron with the arrow going up, the first electron with the arrow going up, and the second electron, I'm going to have the arrow going down. All right, and this is just to show that these electrons in the same orbital have opposite spins. Now, why is this important? Now, remember, electrons are negatively charged. Now, an orbital is a very, very small space. And if you put 2 electrons in this very, very small space, they're going to repel one another because they have the same charge. All right, so to try to overcome this repulsion is that they will spin in opposite directions. By spinning in opposite direction, they will create poles, right? And by spinning that way, they will have opposite poles that will keep them closer together versus if they were not spinning at all. Okay, so this is the reason why. All right, now the last rule that we're going to talk about is what's called the Hund's rule. All right, now Hund's rule basically states that if you have 2 or more orbitals that's within the same subshell energy, okay, each will be filled or will be half filled. Let's use that term. Half filled by 1 electron before any one orbital is completely filled by the addition of the second electron. Okay, now let me make this make sense. Okay, so let's just kind of follow this through. So let's just say we have an atom, okay? The atom of nitrogen. Nitrogen is a good example here. So the atom of nitrogen, a neutral atom of nitrogen, contains 7 electrons, 7 protons, 7 electrons. All right, and so we were trying to figure out exactly how the electrons configure themselves around the nucleus of nitrogen. All right, and so kind of following the rules that we talked about earlier. All right, so we're going to show the 7 electrons to full. So the first 2 electrons are going to be, and I'm going to kind of I'm going to zoom on this. Okay, so the first 2 electrons are going to go into the 1s orbital. Why? Just like Aufbau's principle states that electrons always fill the lowest energy possible first, and then they kind of move their way up. Okay, now Pauli exclusion principle tells you that 2 electrons will fit into an orbital, but if they do, all right, they must have opposite spins. So this is why I have the first one here with this up arrow. My second one has this down arrow. Once the 1s orbital is full, then you got to move up an energy level, because the one shell, or the one shell is completely full with its 2 electrons, like we talked about earlier. All right, and so we got 2 electrons down. Remember, nitrogen has 7, so we have to figure out where the other 5 configure themselves. Well, after the 1s, you move up an energy level, just like we mentioned in Aufbau's principle. Then we move on to the 2s. The 2s is the next energy location, or next orbital location for electrons. All right, and so how many electrons could fit in the 2s? Well, we could fit 2, because it's just one orbital. 1, 2. So here, then we have the next 2. All right, so remember, nitrogen has 7 electrons. Now we found a home for 4 of them. Now we just got to find a home for the last 3. Now what Hund's rule is basically saying is that because electrons, they repel each other. All right, if you have multiple orbitals within the same subshell, all right, subshell energy, electrons prefer to be by themselves. Okay, so this simply means with these 3 electrons that we have left, what you're going to do, you're going to draw 1 electron here on the first orbital, another electron in the second orbital, and another electron in the third orbital. Okay, and so this is the proper configuration of these electrons. Why? Electrons prefer to be by themselves. Okay, and then only, all right, I apologize, kind of tongue-tied there. Then only if you have an electron in each of the orbitals that's within that subshell, then if you add more electrons, then at that point you will double. All right, and so what do I mean by that? So let's look at, for example, oxygen. Okay, well, oxygen has 8. The neutral atom of oxygen has 8 electrons. All right, and so to re-emphasize this, you have this first one here, number 2, 3, 4, 5, 6, 7, and the last electron is going to double the first one, and we're going to put it in. We're going to put it as the opposite spin, and so here is our 8th electron. Okay. And so this is the way that you fill up an orbital diagram. All right, so depending on how many electrons you have, you'll fill this up in this complete order. All right, and so let's just do another example. Like, let me just show you a bigger atom so that we can kind of see how all this works out. So let's look at the atom of calcium, right? So calcium, if you look in the periodic table, we see that the atom of calcium has 20 protons. So let's just assume that this is neutral. So 20 protons, thus it has 20 electrons. So now we need to figure out, how do these 20 electrons configure themselves around the nucleus of calcium? Okay, so remember, it has to follow those 3 rules that we talked about earlier. All right, electrons start with the lowest energy level possible, and then they move their way up in a stepwise manner. 2 electrons could fit in an orbital, but it must have opposite spins when you have those 2 electrons in the orbital. And then last 3, if you have a multi-orbital subshell, all right, within the same energy level, you want to put an electron in each of the orbitals first before you double them up. Okay, so as I said, we got 20 electrons. So we'll start with the first or the lowest energy level possible, which is the 1s. So I'm gonna put my first one here, 1, 2. Then I move up. I'm done with my 1s. I'm gonna move up my 2s, 3, 4. I'm done with the 2s. Now we gotta move up in energy. Now we move up in energy. We're going to the 2p. 5. So 2p is a multi-orbital subshell. So I have to put 1 electron in each first, and then I will double them. All right. So 5, 6, 7, 8, 9, 10. Okay. Now I gotta move up in energy. When I move up in energy, when I move from 2p, I can move on to the 3s. 11, 12. All right, I'm done with my 3s. So I'm going to move up in energy. So remember, I moved from 1s to 2s, 2s to 2p, 2s to 3s. 2p to 3s. Now I'm going to move from 3s to 3p. And I will put my electrons in there. And so far I got 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18. I'm done with my 3p now. So now I'm going to move up in energy from the 3p to my 4s. All right. And then 19, 20. All right. So this is the orbital diagram of the atom of calcium. All right. And so you can see how this, this process works. Okay. So let's go ahead and do another example. All right. So let's say we have silicon. Okay. You look at the periodic table, you look for the atomic number, and you see the atomic number is 14. It has 14 protons. The silicon is neutral. So it also has 14 electrons. So now we want to see, and we want to look at exactly how silicon configures itself, or the electrons of silicon configures itself around the nucleus. All right. And so let's go ahead and just kind of follow the same set of rules, starting from the lowest and move our way up. Double the amount of electrons within the orbital, and then make sure if we have multiple orbitals within a subshell, all right, we put 1 electron in there first before we double it. All right. So we have 14. So let's go ahead and start counting. So we have 1, 2. All right. So I'm going from my 1s to my 2s. That's my next energy orbital. All right. And I got 3, 4. Then I move from 2s to 2p. 5, 6, 7, 8, 9, 10. I'm moving from my 2p to my 3s. 11, 12. Now I'm going to move from my 3s to my 3p. 13, 14. So this is the orbital diagram of silicon, okay, with these electrons, okay? All right, so let's look at another example. So let's say that we were trying to figure out the orbital diagram, or the how electrons configure around the atom of vanadium. All right, so vanadium, its atomic number is 23. So you can look at the periodic table and you see that it's 23. All right, so it's a neutral atom, so it also has 23 electrons. All right, so kind of follow me on this one. There's something that gets a little bit interesting once we get to these type of elements. But as long as you follow the order of energy of how the energy of how electrons fill the orbitals, it's really kind of difficult to get these wrong. Okay, so let's go ahead. So we have 1, 2. Okay, then we move up in energy from 1s to 2s. Then we have 3, 4. Move up energy from 2s to 2p. 5, 6, 7, 8, 9, 10. We go from 2p to 3s. That's the next energy orbital. 11, 12. Then we move from the 3s to the 3p. 13, 14, 15, 16, 17, 18. All right, next up in energy is the 3p to the 4s. 19, 20. All right, now pay attention to exactly how the energy of the orbitals increases in this orbital diagram. All right, from the 4s, the next set of orbitals that goes up in energy is actually your 3d. Okay, because if you notice, if you look at here, all right, your 3d is actually lower than your 4p. Okay, and your 3d is actually slightly higher than your 4s in terms of energy. And remember, the first rule of this is that electrons fill in orbitals according to energy. All right, how much energy it has to use if it's within those specific shells, subshells, orbitals. Okay, so now that we're at 3D, so I only have 3 electrons left. 1, 2, 3. Okay, and that's how this works when it comes to your 3D orbitals, your 3D subshells, and stuff like that. So everything needs to go within this order. All right, we're going to go through just one more example, and then we'll call it a wrap of this video. So we're going to draw the orbital diagram for the element bromine, neutral atom of bromine. You look in the periodic table and you see that bromine has the atomic number 35. It's neutral, so it has 35 electrons as well. So let's go ahead and just jump into building this orbital diagram. All right, so we have 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Remember, from 4s, we're jumping to the 3d because that's your next energy set of orbitals. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now from the 3D, we move to the 4P because that's your next set. That's the next highest or next higher set of energy orbitals. 31, 32, 33, 34, and 35. So here is the orbital diagram for the atom of bromine. So now hopefully by this end of the video, you have a good understanding of how to draw orbital diagrams of atoms.